In this section, I'd like to explain the cylindrical coordinate. We consider a three-dimensional space x, y, z. To describe the position of this blue point, we need a three-coordinate x, y, z. Also, we could use the r, theta, and z. So on the xy planes, r is a distance from the center to the projection point on the xy planes. So x is equal to the r cosine thetas, y equal r sine thetas. And we just add the z coordinate in the polar coordinate. This is a cylindrical coordinate. So equation for the r is expressed as x squared plus y squared. Tangent theta is equal to the y over x. And g equals g. So we add only the g in the polar coordinate. So to express Laplacian cylindrical coordinate is very simple. First three terms comes from the polar coordinate. And we add the last single terms, second derivative of u with respect to g. This term is added in the Laplacian in the cylindrical coordinate. In the next section, I'd like to introduce a spherical coordinate. To describe the point in the 3D space x, y, z, we could use r, theta, phi. Theta is the angle between the z-axis and the radial vectors. And the phi is the angles between the x-axis. So we could convert from the r, theta, phi to the x, y, z using this equation. X equal r sine theta, cosine phi. And y equal r sine theta, sine phi. And z equal r cosine theta. We could convert from the x, y, z to the r. R is expressed square root x squared plus y squared plus z squared. This is the distance from the point to the origins. And the cosine theta is expressed as g over r. So this is equal to g over square root x squared plus y squared plus z squared. If you know the x, y, z, we can calculate the cosine theta. And the cosine phi is expressed x over square root x squared plus y squared. So if you consider this triangle, this is x, this is y, this is square root x squared plus y squared. Then you could calculate cosine phi from the x and y's. From these equations, we could calculate round r, round x. You can perform the partial derivative with respect to x. It becomes x over r. So it becomes sine theta cosine phi. Also, you can easily calculate partial derivative with respect to y. It's a y over r. And sine theta, sine phi. And round r, round z. Z over r is cosine theta. First three equations using this method. To find out the partial derivative of theta with respect to x, y, z, we use this second equation. So by the partial derivative of the second equation with respect to x, it becomes minus sine theta, round x, because the partial derivative of the cosine theta with respect to theta becomes a minus sine theta. And the right hand side becomes minus 1 over 2 and g over x squared plus y squared plus z squared and 3 over 2. And by chain rules, you need to find out the partial derivative with respect to x of the x squared plus y squared plus z squared. It becomes 2x. Then it becomes minus xg over r cubed. From this equation, you can find the round theta round x. It becomes, by substitute x and y, express the r theta phi. It becomes cosine phi cosine theta over r. Also, you could perform the same calculation for the round theta round y. It becomes sine phi cosine theta over r. Same calculation. Round theta round z becomes minus sine theta over r. So we can find out the second column of equation. To find out the partial derivative of phi with respect to x, y, z, we use a third equation. So partial derivative with respect to x becomes a minus sine phi round x equal 1 over square root x squared plus y squared. And 1 over 2 x over, this is x squared plus y squared, 3 over 2. And apply the chain rule, it becomes 2x. 2 is going to be cancelled out. So y square over x square plus y square 3 over. So from this equation, you can substitute expression for the y and x expressed with the r theta phi's. Round phi, round x becomes minus sine phi over r sine theta. So with the same type of the calculation to find the round phi, round y, cosine phi over r sine theta. And the round phi, round z equals 0. Then we could obtain this equation. Then we'd like to find out the derivatives in the spherical coordinate. Round u, round x, we use a chain rule. Round u, round r, round x. Round u, round theta, round x. Round u, round phi, round x. Then we have already calculated. So this corresponds to the round r, round x. This corresponds to the round theta, round x. Last one corresponds to the round phi, round x. Also, you can calculate the same ways for the round u, round y, round u, round z. So we obtained first derivative of u with respect to x, y, z. Then we keep calculating the same way to find the second partial derivative of u with respect to x. It's a really complicated equations for the second derivative of u with respect to x. Also, you could perform the similar calculation to find the second partial derivative of u with respect to y, expressed this one. And also the second partial derivative of u with respect to z in the same way. Then we could calculate Laplacian in spherical coordinate. This is a Laplacian in the spherical coordinate. So we are going to use these Laplacians when we'd like to solve the Laplace equations in the spherical coordinate. Okay, this is the end of this session.